Okay, in today's lecture we're going to cover the section 11.3 material on rates of change. Now, we would define the average rate of change of a function, f of x, as the value of x changes from a to b as the following quotient. We would take the difference in the value of the function at b and the value of the function at a, and then divide by the value b minus a. So this numerator gives us the difference in the values of the function at x equals a and b, and then we divide by the difference in the x values a and b. So let's think about how we could interpret the average rate of change geometrically. So geometrically, the average rate of change defines the slope of the line passing through the points a, f of a, and b, f of b on the graph of some function. So let's see if we can visualize this. So let's suppose that we have the graph of some function, say y equals f of x, so the average rate of change of our function as x changes from a to b could be interpreted as follows. So let's say that we have a x value a, then the corresponding point on the graph of our function for that x value would be a, and since the point lies on the graph of our function, its y-coordinate is given by f of a, the value of the function at x equals a. Now, if we take a change in the value of x, and we change x from a to b, the corresponding point on the graph of our curve would be the point b, f of b. So the average rate of change defines the slope of the line that passes through those 2 points, my line shown in blue here. Because, recall, the slope of a line passing through 2 points is given by the difference in the y values of those 2 points, so f of b minus f of a, for the difference in our y-coordinates, and then we divide by the difference in our x-coordinates, which were b and a. So we're dividing by b minus a. So this rate of, or this slope, is the average rate of change of our function on the interval from a to b, or as x changes from a to b. So now that we have a definition of an average rate of change, let's look at some examples where we'll find the average rate of change of a function. So in these examples, we're asked for the average rate of change of each function over the indicated interval. So in part A, we have f of x is 4x squared minus 6 on the interval from 1 to 5. So that is as x is changing from 1 to 5. So by definition, the average rate of change of the function over this interval would be the difference in the value of the function f of 5 and f of 1. And then we would divide by the difference in the x values, 5 minus 1. So for our numerator, when we evaluate our function at 5, we have 100 minus 6, or 94. Minus, when we evaluate at x equals 1, we have negative 2, so we're subtracting negative 2. And then we divide by 5 minus 1, which is 4. So this gives us 96 divided by 4, which reduces to 24. So 24 would be the average rate of change of our function over the indicated interval. So let's look at part B. Part B, we have f of x is the square root of 3x minus 2 on the interval from 2 to 6. So our average rate of change, by definition, is f of 6 minus f of 2 divided by 6 minus 2. So evaluating our function at x equals 6, we would have the square root of 18 minus 2, or the square root of 16, which is 4, minus the square root of 6 minus 2, or root 4, which gives us 2. And then we're dividing by 6 minus 2, which is 4, so we're left with 2 divided by 4, or if we simplify, 1/2. All right. So, as we mentioned, a geometric interpretation for the average rate of change is the slope of a line through 2 points which lie on our curve. Another way which we could describe the average rate of change, say with words, in this first example, part A, we would say as x changes from 1 to 5, then the function f of x is increasing by 24 units. The difference in the values of my function were positive 24. In this second part, part B, for this function, as we increase the value of x from 2 to 6, the values of our function f of x increase by 1/2. All right. Now, what we're going to be interested in a little bit later in Chapter 11 and throughout the remainder of Chapter 11 and 12 is the concept of an instantaneous rate of change of a function at a point. So in this next part of our section, instead of an average rate of change, we will be referring to an instantaneous rate of change of some function f of x at a value x equals a. And this instantaneous rate of change of a function at a is defined by the following. We have the limit as h approaches 0 of the difference f of a plus h and f of a divided by h, provided that this limit exists. So an instantaneous rate of change is going to be defined in terms of a limit. And from our first couple of sections of Chapter 11, we saw that some limits don't exist. So this instantaneous rate of change of a function, which is defined in terms of a limit, is defined only as long as this limit exists. So let's think about a geometric interpretation of an instantaneous rate of change and see where exactly this formula is coming from. So geometrically, we would say that the instantaneous rate of change is representing the slope of the line which lies tangent to the curve y equals f of x at a point a f of a. So let's think about this visually. We have some function y equals f of x. So let's consider its graph. And let's say that I choose some point on the graph of my function corresponding to a specific value of x, let's say x equals a. So this point on the curve would have an x-coordinate of a, and the y-coordinate would be given by f of a, since it lies on the graph of this function. So if we consider a line which passes through that point and is increasing at roughly the same rate at which our function is increasing at that point. So for this point, we see that our curve seems to have this sort of small slope. So if we consider the line passing through that point, which has this slope, this is called a line tangent to the curve. And I claim that this instantaneous rate of change is the slope of that tangent line. It's telling me how fast my function is changing at a particular instant. That is, when x is equal to a, or at a particular point on our curve, what the slope of our curve is. So let's think about how we could find this. Now, we don't know how to find the slope of this line directly at this point, but what we had seen in the first part of this section is how to find the average rate of change. So let's say that I chose another point on my curve. Let's say I choose another value of x, maybe something a little bigger than the value x equals a. Let's call it a plus h. So I can find the corresponding point on my curve as having an x-coordinate of a plus h and a y-coordinate as the value of the function at that x value. So f of a plus h. And I know how to find the slope of the line which passes through those 2 points. So that would be given by the average rate of change of the function from a to a plus h. So that's the difference in the values of our function at a plus h and a. And then we divide by the difference in our x values, which were a plus h and a. So in our denominator, we see that this plus minus a term cancel, and we're left with f of a plus h minus f of a all over just h. So that gives me the slope of my line shown in red here. Now, in the definition of our instantaneous rate of change, we're taking the limit of this slope as h approaches 0. So recall h is the distance which I've moved to the right of the value x equals a to get to a plus h. So as h starts shrinking to 0, I'm moving these 2 red points on my curve closer together. So as h gets smaller and I move these 2 points closer to each other, I start getting lines whose slopes are approaching the slope of this blue line which lies tangent to my curve. So here the initial red line that I had was the following. If I make h a little smaller, I have the following line, which is a little closer to the blue line. And if I keep shrinking h towards 0, that is, if I'm moving these 2 points closer together, eventually the slope of my line is approaching the slope of this blue line, which I was interested in. And that's giving me how fast my function is changing at this point a, f of a on the graph of our function. So we're going to take the limit as h approaches 0 of this quantity to be the instantaneous rate of change as long as that limit exists. So now that we've defined an instantaneous rate of change and seen a geometric interpretation, let's look at some examples. So in this first example, we are asked for the instantaneous rate of change of f of x is x squared plus 3x plus 1 at x equals 1. So by definition, the instantaneous rate of change at x equals 1 would be the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. So here, why are we using a as 1? Well, here we're looking for the instantaneous rate of change at x equals 1. In general, our formula was for x equals a, so a is 1 in this example. So let's see if we can evaluate this. Here we're looking at the limit as h approaches 0 of f of 1 plus h. So we're going to take our function f of x, and everywhere we had an x, we replace it with 1 plus h. So we're going to have 1 plus h squared plus 3 times 1 plus h plus 1. And then we're subtracting the value f of 1. So if we evaluate our function at x equals 1, we have 5. And then we're dividing the whole thing through by h. So let's see what this gives us. We have the limit as h approaches 0 of, in the numerator, if I expand my 1 plus h quantities squared, I have 1 plus 2h plus h squared, plus, if I distribute the 3 through the 1 plus h, I have 3 plus 3h, and then my plus 1 minus 5. And then the whole thing is still being divided by h. So let's see what simplifies here. In our numerator, we have a constant 1 plus 3 plus 1, which would be 5, and then I'm subtracting 5. So these constant terms cancel. Let's see what else we can group together. I had a 2h plus a 3h will leave me a numerator of 5h, and then plus we have this h squared term. So my numerator becomes 5h plus h squared, which we're then dividing by h. And so dividing my numerator through by h, we have the limit as h approaches 0 of 5 plus h. So now in my last step, I'm taking a limit of a polynomial function as h approaches 0. We know the limit of a polynomial we can find by simply plugging in the limiting value of h. So plugging in 0 for h, we're left with a value of 5. So what this means is that when x is equal to 1, this function, f of x, whose rule is given here, is increasing at a rate of 5 units. So at that particular x value, our function is increasing by 5. All right. So let's look at another one, sort of similar. In this next example, we have a pretty similar function. F of x is some quadratic. And we're going to try to find the instantaneous rate of change of this function at a particular x value. But here, we're breaking up the problem into smaller pieces. Some of your homework problems make use of this. So here we have the function f of x is the following. And in part A, we're supposed to find f of a plus h and simplify completely. So here, in order to find f of a plus h, we take the function, and everywhere that we have an x, we replace it with a plus h. So expanding our a plus h squared term, we have 2 times a squared plus 2ah plus h squared. Plus, when we distribute our constant 2, we have 2a plus 2h, and then minus 1. Now, if we distribute the constant 2 out in front, we have 2a squared plus 4ah plus 2h squared plus the rest of this. We still had our plus 2a plus 2h minus 1. So in part A, we found f of a plus h in simplified form is the following. Now in part B, we are asked to find f of a plus h minus f of a and simplify completely. So here, f of a plus h minus f of a is given by, well, we just found f of a plus h in part A of this problem. We found it to be 2a squared plus 4ah plus 2h squared plus 2a plus 2h minus 1, and I'm subtracting f of a. That is the value of my function when x is a. So replacing x by a in the definition of our function, we have 2a squared plus 2a minus 1, and I'm subtracting that quantity. So let's see what we're left with here. Certain terms cancel, namely our 2a squared and then our minus 2a squared will cancel. We had a plus 2a, and then we are subtracting 2a, so our plus minus 2a cancel. And then our constant, this negative 1 on the end, and then we were subtracting a negative 1 or adding 1, so those constants cancel. And we're left with 4ah plus 2h squared plus 2h, and this would be the expression we were asked for in simplified form. So in part C, we then ask for f of a plus h minus f of a, that is what we just found in part B, all over h, and simplify completely. So here, the value that we're interested in, f of a plus h minus f of a all over h is given by, well, our numerator is what we just found in part B. It was 4ah plus 2h squared plus 2h, and then the whole thing is being divided by h. So dividing each term of our numerator by h, we have 4a plus 2h plus 2. And in part D, we're asked for the instantaneous rate of change of f of x at x equals 3. So the instantaneous rate of change of our function at x equals 3 is given by the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. So here we're using a value of a equals 3, since that's the value of x that was provided here. Now, the expression that we're taking the limit of is what we found in part C, but with a being set equal to 3. So using the work that we had found in the previous parts of this example, we have the limit as h approaches 0 of, from part C, we had 4 times a, so if a is 3, we have 12, plus 2h plus 2. So taking a limit as h approaches 0, well, this 2h term, when we plug in 0, has a limiting value of 0, and we're left with 12 plus 2, which is 14. So for this function, the instantaneous rate of change at x equals 3 is given by 14. Okay. Now, some applications of average or instantaneous rate of change are what we're going to consider next. Starting with a physical interpretation, if we have an object which is moving along a straight line. So let's introduce the following definitions. Suppose that we have some object which travels along a straight line. So maybe we could think about a car or a person traveling along a straight segment of road, or we could think about a ball which is thrown directly upward or dropped so that it's falling directly downward in a straight line. And we would say that the position of our object at time t is given by a function s of t. So typically in calculus, you'll see s of t as representing a position function, where t represents time. So two definitions that we'll give, the first of which is the average velocity of our object over a time interval from t equals a to t equals b is given by the average rate of change of our position function over that time interval. That is s of b minus s of a over b minus a. So let's think about what that represents physically. We're taking our position at time b minus the position at time a. So this is the total distance that we've traveled in that time interval. And then we are dividing by b minus a, the difference or the amount of time which has passed. So the distance traveled divided by the time which has passed will give us our average velocity over that time interval. Now we can also define the instantaneous velocity of our object at any time, say t equals a, as the instantaneous rate of change of the position function s at time a, provided that that instantaneous velocity, which is a limit, exists. So instantaneous velocity would tell us how fast an object is changing its position at one particular instant. So let's look at an example working with average velocity versus instantaneous velocity. So here we will say that we have a car which is traveling along a straight road, and its position in feet after t seconds is given by the position function s of t is 3t squared plus 2t. And in part A, we are asked to find the average velocity of our car over the time interval, t equals 5 to t equals 10. So the average velocity would be given by the difference in our position s at time 10 and at time 5. And then we divide by the amount of time which has passed, so difference between 10 seconds and 5 seconds. Now, evaluating our function s at t equals 10, we have 300 plus 20, so 320, minus, if we evaluate our function at 5, we have 75 plus 10, so 85. And then we're dividing by 10 minus 5, which is 5. So this leaves us with 235 divided by 5, which reduces to 47. And let's think about what units we're using here. Since distance was measured in feet, our numerator is measured in feet, and then we're dividing by a difference in time, which was being measured in seconds. So here we would have 47 feet per second. So the average velocity or average speed of this car in the time interval between 5 and 10 seconds is 47 feet per second. Now in part B, we ask what is the average velocity of this car over the time interval from t equals 5 to t equals 6. So we're shrinking the length of our time interval now. Instead of from 5 seconds to 10 seconds, now we're looking from 5 seconds to 6 seconds. So our average velocity would be the value of our position at time 6 minus the position at time 5 divided by the difference in our time, 6 minus 5. So evaluating our function at 6, we have 36 times 3 plus 12, which leaves us with 120, minus, when we evaluate our function at t equals 5, what we already found in part A, that gives us 85, and then divided by 6 minus 5, which is 1. So we're left with 120 minus 85, which is 35 feet per second. So the average velocity of our car between time 5 and 6 seconds would be 35 feet per second. Now, in part C, we're asked for the average velocity of this car over the time interval from 5 seconds to 5.1 seconds. So over a very short time interval, from 5 seconds to 5.1 seconds, we want our average velocity. So here we would have s of 5.1 minus s of 5 divided by 5.1 minus 5. So in our numerator, when we evaluate s at 5.1, we have 3 times 5.1 squared plus 2 times 5.1, which gives us 88.23. We can evaluate that using a calculator if we wish, minus the value s of 5, which we've already found to be 85 in parts A and B. And then we're dividing by 5.1 minus 5, which is 0.1. So this leaves us with 3.23 divided by 0.1. So that's dividing by 1/10, or equivalently we could multiply the numerator by 10, and we're left with 32.3 feet per second. All right, so if we consider a very small time interval moving forward from 5 seconds, we see that our average velocity is about 32.3 seconds. So what we found in the first few parts of this problem is an average velocity over a time interval starting at time 5 and then moving forward in time over smaller and smaller time intervals. So the values that we found for the average velocity in parts A, B, and C are approximations of the instantaneous velocity of this car at time 5 seconds, because we're shrinking the length of our interval down to essentially a single point in time, t equals 5. So based off of the results that we found, starting with 47, then 35, then 32.3, we might suspect that our instantaneous velocity of the car at 5 seconds would be 32 feet per second. So let's see if we can establish that. In this next example, we have the same problem. A car is traveling along a straight road, and its position in feet after t seconds is given by this position function 3t squared plus 2t. And we are asked to find the instantaneous velocity of our car after 5 seconds. So here, our instantaneous velocity after 5 seconds would be the limit as h approaches 0 of s of 5 plus h minus s of 5 all over h. So that is the limiting value of our average velocity from time 5 to 5 plus h, as that value h is getting smaller and smaller. So let's see what our limiting value would be. So here we have the limit as h approaches 0, and s of 5 plus h is found by taking 3 times 5 plus h squared plus 2 times 5 plus h. So that is evaluate our position function at t equals 5 plus h. Then we're subtracting s of 5, which in the previous example we found was 85. And then we are dividing the whole thing through by h. So this gives us the limit as h approaches 0 of 3 times. If we expand 5 plus h squared, we have 25 plus 10h plus h squared, plus if we distribute the 2, we have 10 plus 2h minus our 85, and then the whole thing is being divided by h. So let's see what we have. We've got the limit as h approaches 0 of, in the numerator, if I distribute the constant 3, I have 75 plus 30h plus 3h squared plus 10 plus 2h minus 85 all over h. So let's simplify in our numerator and see which terms will cancel. So here, grouping our constants, we have a 75 plus 10 is 85, and then we're subtracting 85. So our constants will cancel here. Now grouping the h terms, we have 30h plus 2h, which leaves me with 32h, plus we have this 3h squared, which is then being divided by h. So that leaves us with the limit as h approaches 0 of 32 plus 3h, dividing our numerator through by h. And now, as h approaches 0, well, this second term, 3h, has a limiting value of 0, and we're left with the limit of a constant 32, which is 32, being measured in feet per second here. So our intuition from the previous example was correct. As we're looking at the average rate of change over shorter and shorter time intervals, starting from time 5, we saw our average rate of change seem to be getting closer to 32, and by evaluating this limit, we see that indeed the instantaneous velocity of our car after 5 seconds is 32 feet per second. Now, in this last part of our section, we'll introduce some terminology that we had briefly discussed in Chapter 3 when we were talking about applications of linear functions, but we're going to generalize the definition that we had introduced there. Some important terminology which we'll use throughout the course, which appears in business and economics, is the rate of change of a cost revenue or a profit function. So the rates of change of variables such as cost, revenue, or profit are important considerations. Now, in economics, they use the word marginal to refer to rates of change. So when we talk about a marginal cost, marginal revenue, or marginal profit, we're talking about the rate of change of those quantities. So if we have a function, let's say c of x, which represents cost, so we would have a cost function, the marginal cost would refer to the instantaneous rate of change of that cost function. Similarly, the marginal revenue or marginal profit refer to the instantaneous rates of change of the revenue or profit functions. So something to keep in mind for this course is any time that you see the word marginal being used, that means rate of change. So keep in mind marginal is a term used for rate of change. So now that we know how to find instantaneous rates of change, let's look at some examples related to economics. So say that the cost in hundreds of dollars of manufacturing X units of some product is given by the following cost function, where the number of units produced, X, can range from 0 to 20. So in part A, we are asked to find the average rate of change of the cost function when production is increased from 5 to 10 units. So the average rate of change of a function is given by the quotient, where we evaluate our function, in this case c, at 10, and subtract c of 5. So it's the difference in the cost of producing 10 units versus 5 units. And then we divide by 10 minus 5, the difference in the number of units that we're producing. So here, evaluating our cost function, c, at 10, we are left with 40 plus 80 would be 120, minus our 0.2 times 10 squared, or 100, would be 20. So that leaves us with 100. Minus, when we evaluate our cost function at 5, we have 40 plus 40 is 80, minus 0.2 times 5 squared, or 25, which would leave us with 75, all over 5. So here we are left with 25 over 5, or 5. So what that means is if we increase production from 5 units to 10 units, our average change in the cost will be 5, but remember here cost is being measured in hundreds of dollars. So we would see an increase in our cost averaging $500. Now in part B, we are asked to find the marginal cost, that is the instantaneous rate of change of the cost function when we're producing 5 units. So recall that our instantaneous rate of change is defined as a limit. The limit as h approaches 0 of c of 5 plus h, since we're interested in the instantaneous rate of change when we're producing 5 units, minus c of 5 over h. So let's see what we have here. We have the limit as h approaches 0 of c of 5 plus h would be 40 plus 8 times 5 plus h minus 0.2 times 5 plus h quantity squared, minus c of 5, which in part A we found was 75, all over h. So let's simplify. We have the limit as h approaches 0 of, in the numerator, 40, plus, if we distribute the 8, we have 40 plus 8h, minus 0.2 times, expanding our 5 plus h squared, we have 25 plus 10h plus h squared minus 75, all over h. So we have the limit as h approaches 0 of 40 plus 40 plus 8h minus, if we distribute our 0.2 or 1/5, we would have 5 minus 2h minus 0.2h squared, and then our minus 75 on the end, and the whole thing is still being divided by h. So let's see what we can simplify through our numerator. We have 40 plus 40 is 80, minus 5 would leave us with 75, and then on the end we're subtracting 75. So all of our constant terms will cancel here, and then we're left with, in the numerator, 8h minus 2h. So we have the limit as h approaches 0. In the numerator, we now have 6h, and then minus our 0.2h squared. And then the whole thing is being divided by h. So, dividing through by h, we have 6 minus 0.2h, and taking the limit as h approaches 0, we are left with a value of 6. So our cost is increasing by $600 when we're producing 5 units. All right. So in this section, we've introduced the concept of rates of change, either an average or an instantaneous rate of change. And we've seen an interpretation of an instantaneous rate of change as representing maybe the instantaneous velocity of an object moving along a straight line, or as marginal cost, how fast our cost is increasing at a given production.